Hey guys, this video will help you do the worksheet that's due tomorrow. Um, I will post this video with the assignment as soon as I'm done here. It's 9:23. This will take about 10 minutes probably. So what I'm going to do is draw a couple more potential energy diagrams, endo and exothermic, and then review that. I'm going to use table I here to help you understand delta H a little bit better. And then I'm going to label different parts of the potential energy diagram and talk about a catalyst. Tomorrow in class, I will show you some videos from YouTube when you add a catalyst to a reaction or a demo, how it reacts way faster, because that's what catalysts do. A lot of times you guys already kind of know getting to me because of biology. Enzymes are biological catalysts in your body. It's a little different with chemistry as far as instead of in your body, it's with chemicals, in a lab, let's say. But you've heard of catalytic converters, perhaps. I'll talk more about those tomorrow. Show you a little video on that too, what they do for your car and how it's a catalyst. Anyway, so here we go. So I'll come back to this first in a minute here. So we got two types of curves here. So you got, let's say, this one and this one here, both called potential energy diagrams. So potential energy is on the Y, and reaction progress, we'll put here reaction progress or time. Reaction progress here. All right, this one we will start here, go like this, and then come down. And this one we will start here, go like this, and then we'll end up here. So this one is endothermic over here. This one is exothermic. Again, how do we know this? Well, this is always where our reactants start. This is where our products end. Same thing here, reactants here, products here. So, the energy on the y-axis, again, if we make up a scale, 0 to 100, 0 to 100, we can measure the energy of products and reactants. And if the reactants start out with more and the products end up with less, that means it lost energy, right? So again, if we make this, let's say 30, let's say this is in kilojoules, this is in kilojoules. So the products are 30 and the reactants are, let's say, that's pretty close to halfway, 50. So my delta H, which is called the heat of reaction, and I'll write that after this. Delta H is heat of reaction or change in energy. Delta means change. As we progress through this reaction on the left here, it starts at 50, goes over the hill, comes down, ends at 30. So it lost 30. So that would be negative 20 kilojoules. That would be the value of delta H. And where did we get that? 30 minus 50, right? We ended at 30, started with 50. We lost 20, right? It's like you have $50 before you go on a trip, I don't know, somewhere, and you buy some things. You come home and you only have $30 left, right? So you lost $20. So that's negative 20 from your account, let's say, right? If that helps you understand. Over here, it's the opposite. Let's say we start at 50 and we end, here, let me draw a line here. Let's say we end at, I don't know, we'll make it easy, 70. So our delta H here, our change in heat, change in energy here is positive 20 kilojoules because you gained 20, right? So let's say you start with 50, then you walk around on the street and you find a $20 bill. Now you have $20 more, so that's a gain, right? So it's a positive thing. You gain 20. That's because the products are higher in energy than reactants. So I'm hammering this because that's a really important concept. All right. So I wanted to review that with you. Now, as far as what you need to know for the worksheet that's due tomorrow, let me label some more parts to this thing here. So I'll make this bigger. Okay. Well, you know what? Let me make that a little bit. Come on. All right. So we'll make it a little bit bigger. Here we go. All right, we'll make it exothermic, so we'll come up here and then down here. All right, so you really need to know a few things here. You need to know where delta H is. So delta H, Whoa, what am I doing? Delta H is from here to here. That's our heat of reaction, change in energy. So that's maybe zone 1. Zone 2 here is going, remember, here's our reactants, here's our products, would be an arrow going from here to the top. So right here to the top. All right, so that would be zone 2. That would be our activation energy. So I'm going to abbreviate AE. That's activation energy. Energy needed to start a reaction. Right at the top, label that number 3. Number 3 is called the activated complex. That's where collisions occur. That's where the collisions are. If the collisions are effective, enough kinetic energy with proper orientation, they make products. If they don't, then they come back down here. So number 1 is our heat of reaction. RXN is reaction, or change in energy, change in heat, and that's always products minus reactants, always. That's why this is negative. A small number minus a bigger number is negative for exothermic. Number 2, I'll put that up here. Number 2, activation energy. Again, what is that? Energy needed to activate, to start the reaction. So you have to give the reactants enough energy to get up this hill. Once they get to the top, that's called the activated complex. Sometimes it's called the transition state because you're transitioning from reactants to products, and that makes your collision. And if the collisions are effective, then you will make products. And then again, here's your change in your heat of change in energy, heat of reaction. Now, if you wanted to go in reverse, so if you wanted to start here and work your way up this way, you actually would have to climb this mountain here. So number 4 would be, I'm just going to abbreviate, activation energy, but of the reverse reaction. And the analogy I use in class, I pick somebody, right? So I say, okay, let's say somebody is standing here, whoever that could be. I don't know. We'll say that's Paul. And then we got somebody here, and I don't know, let's say that's Lexi, right? And they race up the mountain. So she's running up the mountain, Paul's running up the mountain. So let's say they both run at the same speed, same rate. If Paul and Lexi are running at the same speed, and I'll review this again tomorrow. Obviously, Lexi's going to get to the top first. Why? She has a shorter distance. Her hill is smaller. His is greater, larger, bigger. What does that mean? It means in an exothermic reaction, the reverse reaction always takes longer, because the time it takes for the products to get to the top and start colliding to try and form reactants, because reactants and products, they can make each other. They can go back and forth. You saw that yesterday with the double arrow. That's more in the next unit, but we can go either way with a lot of reactions. Most reactions only go from reactants to products. Why? Well, most favorable reactions are exothermic. And what does that mean? It means it's easier for reactants to get to the top than products. So what I'm trying to get you to understand here is that activation energy of the forward, going from reactants to products, left to right, here is quicker, faster, increased reaction rate, and the reverse is going to be slower, the decreased reaction rate, because it takes them more energy to get to the top. Okay, we could label the y-axis, right, as potential energy, with energy numbers like 10, 50, 100, whatever, and you can see it takes more energy to get to the top. We'll talk more about this tomorrow when we go over those 2 worksheets, the one due yesterday and the one due tomorrow. So these are the main numbers or zones that you need to know. Delta H is the difference between reactants and products energy, and that delta H corresponds directly to these delta H's right here. Okay, so this one loses 890. This one loses 2,000. This one loses 1,000. So these are measured just like this, the difference between reactants and products. All right, so that's important, understanding where activation energies are, whether it's forward or reverse. And then right at the top, it's called activated complex. Okay, so let me clear that. Let me draw another one here. So now we'll take one, and I'll show you what a catalyst does. So a catalyst speeds up a reaction. And how does it do that? It lowers activation energy. That's it. It allows the reactants to react with less energy. It provides another pathway, an alternate pathway. What does that mean? It's like a shortcut. Shortcut. So if we're standing here, okay, and we take the normal path up to the top, and this is where reactions and collisions occur, and we continue on to make products, a catalyst actually does this. So a catalyst comes in here. You know what? Let me use a different color. Maybe that'll be more fun and easier to see. All right, so we'll use this color. So a catalyst does this. Oh, that's good enough. It's not supposed to cross the line there. So basically, if this person here wants to get here faster, they would take the purple, pink line, whatever. If they want to take longer, they take the blue. So a catalyst lowers this peak, right? So this represents a catalyst. That's what that is. That's how you draw a catalyst on these diagrams. So the original activation energy is from here to here. There's the original activation energy. Let's say it's 50 to 90. So that's 40, right? You need 40 kilojoules to get to the top. Well, if you take the catalyst's route, so the shortcut, let's say that's 70, right? So from here, from 50 to 70, you only need 20 kilojoules. So because the reacting particles need less energy to get here, they react faster, collide faster, more effectively, quicker, and they make their products quicker, faster. So that increases reaction rate. That's how we say it. That means it reacts faster. So that's it. That's what a catalyst does. It lowers that activation energy, provides a shorter alternate pathway for reacting particles to collide up here and make their products. That's what catalysts do. And the nice thing about a catalyst is you can reuse it over and over and over and over again. All right, catalysts don't actually take part in a reaction. Okay, so if you had a reaction like A plus B yields C, and you put a catalyst in here, you wouldn't see it here or here. Okay, the way you would show it is actually you would write it above the air. I'll talk more about that tomorrow, maybe. That's not something we necessarily need to fully get into. But basically, catalysts are never reactants or products. They just help. So I use the analogy, catalysts are like teachers or coaches. I can't take the test. I can't learn it for you. I can't play in the games for my players, but I can help, right? So hopefully help, right? So that's what catalysts do. They help these reactions work faster, and it works both ways. If I'm starting here, I want to take the shortcut back the other way. So the forward and reverse both react faster. Why? Because the catalyst is there to help. Helps them have an alternate pathway which needs less energy to react. So that's what catalysts do, and I'll talk more about that tomorrow. That should be enough info for you to do the sheet due tomorrow. So I will stop. Hopefully this isn't too long. Let's see. Okay, not too bad, 13 minutes. All right, I'll see you guys tomorrow.